an example of seating students in a row is a nice way to illustrate how permutations work. The first example I'll give is just how many ways are there to seat 10 students in a row, where the order would change, would make it a different seating. This we could do without permutations. We could write this as, do the first. There are 10 ways, 10 students we can put in the first seat. And then the second one, there are 9 students to put in the second seat, all the way down to 1 in the 10th seat. Well, that's recognizable, I think, as 10 factorial. And what that illustrates is that P10, 10, which is permuting all 10 of them, and the number of ways we could do that is simply 10 factorial. And in general, we have that Pn, n, the number of ways to permute n distinct objects, is simply n factorial. So that's a nice one to have on its own. Pops up plenty in what we'll do. In fact, we'll use that in the next problem here, where we're asked to talk about seating 10 students in a row. If 5 of them are boys and 5 are girls, how many ways are to seat them so that the boys are together and the girls are together? That is to say, we have 5 boys in a row and 5 girls in a row. So I guess what we could do is say, well, let's see, we could have this scheme here. We could have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we'd have the 5 boys and the 5 girls. And we could have any of the 5 boys first, and then 4, and then 3, and then 2, 1, 2, 1, like so. And now let's seat the girls. Well, there's 5 choices here, so that's the first girl. And then the 4 girls remain for the next spot. We have 3 choices of girls for the next one, and 2, and then 1. So it looks like 5 factorial times 5 factorial. So think about that. Is that it? Is it just 5 factorial times 5 factorial? If you want to pause and think about it, that's fine. Okay, so I guess we could have started it with it this way too, right? Girls first and boys second. And so here we'd have 5 factorial and 5 factorial that way. And so in fact it is 2 times 5 factorial, 5 factorial. Okay, 2 5 factorial squared. Let me just leave that one out and rewrite that one so it doesn't look so crummy. 2 times 5 factorial, 5 factorial, the product of those things right there. Okay, well, what if the boys and girls alternate? Well, does it matter, really? I mean, in this case here, we could have first boy, there's 5 ways. First girl, 5 ways. Second boy, 4 ways. Second girl, well, there's 4 girls that remain. 3, 3, 2, 2, 1, 1. Turns out the same thing. And we could have started with girls. First girl, 5. First boy, 5, etc. to 1 times 1. So again, we get 2 times 5 factorial, 5 factorial. Now there's a couple more problems down here, and we're going to do those in class, so I'm going to skip them around. Skip around that one. I guess there's just one there. Yeah. But I do want to talk about a notion of circular permutations. In circular permutations, what we're saying is we're seating people around a circle, and we will distinguish those seatings if the relative positions change. You know, if the person on your right and left change, or one of them, or they change in the way they are arranged right and left around you, then that's a different arrangement. But otherwise, they're the same. So in particular, if we just take 4 of them, then if we take A, B, C, D around a circle, A, B, C, D around a circle, that's the same as putting the B up here, and then we'd have C here, and D here and A here, where I rotated it, I guess, counterclockwise, right? Those are the same. So another way to look at that is the first one we might write it as A, B, C, D going around the circle clockwise, and then this would be the same as if we had B, C, D, A, where we took the A and put it over here, and this would be the same as if we have C, D, A, B, where we took the B and put it over here, and this will be D, A, B, C, again moving the C over here. Oh, there's 4 ways to do that. There's 4 ways to rotate around the circle, or 4 ways to rotate in this way, and have the same relative positioning of people. So the answer for this would be 4 factorial divided by 4, or 3 factorial. And in the general case where we have 6 friends, there are 6 factorial ways to arrange them, but for each of those there are 6 ways to rotate around the circle without changing relative positioning, so that there are only 6 factorial divided by 6, or 5 factorial distinguishable arrangements. This one was D, A, B, C, just to keep that in there. So in the general form, the number of permutations of n objects around a circle is n factorial divided by n, which is n minus 1 factorial. Okay. Now there's some other things we can do with this, and we'll do that in class. But that's how circular permutations work out, because you can take any arrangement and rotate it around the circle n times without changing relative positioning. So things are grouped in that particular way. Okay, so that's a good place for us to stop, I think.